So let's continue our topic. Yeah. Here, there is another important concept I want to spend some time to explain. That's the invertibility of matrices. Yeah. Yeah. All right. First, let me talk about this general invertibility issue in mathematics. In math, invertibility concept is very important. Yeah. So far, actually, we have learned a lot of inverse objects. Yeah. So we have at the beginning, we have some mathematical objects. Yeah. Those objects, there exists their inverse mathematical objects. Let's review a little bit. Yeah. We have several such objects. Yeah. All right. One is Laplace transform, the inverse Laplace transform, right? Yeah. So Laplace transform, so it's a transform. Okay. That object is a transform object, but that object, there exists inverse Laplace transform object. That's one. Okay. All right. Then another mathematical sine function, inverse sine function, right? Yeah. So another object, sine function, inverse arcsine, right? Arcsine. Some people write inverse. Yeah. Some people write a, inverse like this, sine inverse. Yeah. Inverse. But usually I try to, because this notation, it's very easy, people confused with reciprocal, 1 over sine, then you get it wrong. So to avoid that confusion, I like to write arcsine. Then you will not understand 1 over sine. It's not a 1 over sine function. All right? Then e function, right? Exponential e function, e to the x. It's inverse log, natural log. See? Natural log. Right? So all these invertible objects. Yeah. And what's the relationship? Because when we talk about, so these objects, they are inverse each other. What is the relationship? Yeah. Important relationship. Okay. All right. For example, for Laplace transform, if you apply Laplace transform on a function f, then you apply, after that you apply inverse Laplace transform. You recover the original function. That's one. Then the other way around. Yeah. All right. Yeah. Let me use g function. Okay. Capital. Yeah. Our inverse we apply on capital function. Right. So you apply inverse Laplace transform on capital F function. After that, you apply Laplace transform on that result. You get a capital F, right? Same function. Okay, that's inverse, right? Yeah. Then sine, you also have that. Yeah, but you need to consider the domain sine, because when you consider inverse, it must be in appropriate domain. Yeah. All right. So here, e function. Yeah. So I skipped the sign. Okay. All right. Yeah. But you have the similar relationship. For the e function, we can do two way. Okay. Natural log of e to the x. What's that? The same as x, right? Yeah. Natural log e, like some cancellation. Only x left. Yeah. That's one. Another is you take e function, exponent natural log also x, right? Yeah. So you recover the original x number in using these two ways. Okay. Change the order. That inverse. Yeah. There is another inverse you may not notice in our multiplication. Yeah. In our arithmetics, we do multiplication, scalar multiplication specifically. Suppose you have an a number. Your a number is not equal to 0. then there is an inverse of this A number. Yeah. Can you see it? Yeah. With respect to multiplication, there is an inverse. That is the reciprocal of A. Yeah. 1 over A is the inverse of original number, non-zero number A. Okay? Because here, why you say 1 over A is an inverse of A? Because you can use A multiply 1 over, that's 1. Okay? That's 1. 1 is the identity number, right? Identity object. Because 1 times any number, still that same number. You do not change it. So 1 is the identity object. Then here you change the order, 1 over A times A, also that 1 number. Okay? From these two relationships, you can see, yeah, they are inverse each other. A and 1 over A, they are inverse each other. All right. Now, we want to go to the matrices. Yeah, we want to, extend this invertibility concept to matrix algebra. Yeah. In matrix, do we have an inverse matrix, right? Yeah. So if our original object is a square matrix object, yeah. Here we use 2 by 2, but in general, a square matrix object. Is it possible we can find an inverse matrix such that, yeah, because if you find an inverse matrix, to matrix multiplication, you should get an identity matrix, right? Yeah, based on our, observation we just did. All right, now, yeah, so we can consider the inverse matrix. Yeah. Here, there is a linear algebra result. If A is invertible, yeah, if you know A is invertible, then A times x equals 0 implies that A equals 0. Yeah. Why? It's very simple. Yeah. Because what do you mean A is invertible, right? Yeah. A invertible means A inverse exists, right? A inverse exists. Yeah. So you can find another special matrix. That matrix, yeah, is the inverse of A. So what do you mean? Inverse matrix. Yeah. So you can find that special matrix. If you do matrix multiplication, A times A inverse, you will get identity matrix. Yeah, here could be n by n. Yeah, not necessarily 2 by 2. Okay. Yeah, n by n identity matrix. Yeah. Then, if you change the order, yeah, if you use inverse multiply the A matrix, you also get identity matrix. Okay. Yeah. So that's the meaning of inverse matrix. The main property. Yeah. Inverse matrix. Here, all right, now you know A is invertible. That means its inverse exists. Okay? Yeah. A inverse exists here. If it exists, you can multiply in A inverse both sides, right? Inverse, both sides, inverse. Inverse, right hand side, you multiply inverse with 0 vector, it's a 0 vector. But left hand side, A inverse multiply A, it's identity matrix, right? So A inverse, the product is identity matrix. Then identity matrix multiply X, still X, right? Yeah. So X equals 0. Yeah. So here, this simple result tells you if your A matrix is inverse, then you have a linear system A times vector X equals 0, then this linear system you only have the trivial solution. X equals, it's a trivial solution. That means this linear system does not have non-trivial solution. You cannot find a non-trivial solution. The only solution must be the trivial solution. Yeah, so we use the matrix inverse. This property, it can tell us if the homogeneous linear system has non-trivial solution or not. All right. Yeah. Only trivial solution. Okay, only trivial solution. Yeah. All right. Then, yeah, here I review. If A is invertible, then A inverse exists, and that property. Okay, I wrote that property here. I write it again. Yeah. A times A inverse equals A inverse times A equals that identity matrix I. Yeah. That. In this way, then you can multiply inverse from both sides, left-hand side, right-hand side. Yeah. So you can do manipulations using the matrix inverse. Yeah. If the inverse does not exist, then you cannot do calculation like this. Okay. So the existence of the inverse, it's important. Okay. All right. Then, another thing I want to also, here, because here, I want to talk about another concept. Yeah, it's called a commutability concept. Yeah, I just finished invertibility concept. Now I move to convertibility. Sorry, commutability, not convertibility. Commute. You know commute, right? Commutability. Here I want to talk about commutability. Commutable or not? Okay. Matrix multiplication, commutable or not? Yeah. Because in our scalar algebra, your experience, the product of two numbers is always commutable, right? Yeah. For scalar algebra, AB always equal to BA, right? So this probably tells us the scalar product is commutable. Okay, you can switch the side. Yeah. So scalar scalar product is commutable. Yeah. Addition also A plus B equals B plus A. Addition is also commutable. Okay, addition. Yeah, A plus B, B plus A, commutable. Yeah, but when we move to matrix algebra, in general, you do not have A times B in general is not equal to B times A. Yeah. You select arbitrary two matrices, A matrix, B matrix. In general, they are not commutable. Okay? Yeah. Only in some very special cases, they could be commutable. Yeah. But the general case, not commutable. Okay, yeah. All right. Yeah. But here, why I talk about matrix commutability. Yeah. So here, the rules different, right? Yeah. So you cannot switch the side. The rules completely different. Yeah. In matrix multiplication, you never switch the order of two matrices in your product. Yeah. It's dangerous. Yeah. But here, in this product, A and A inverse, they are commutable. Okay? They are commutable. You can switch. Because inverse is a special case. Okay? So that's commutable. That's commutable. Okay? All right. Yeah. All right. So another. Yeah. Then we go back to our original question. Yeah. This time, lambda times identity matrix, and A matrix minus lambda I2 equals, so we can write this matrix explicitly. Okay? Yeah. write it out. Yeah. Because we want to calculate its determinant. Yeah. Remember, based on this theorem, because we want to look at under what situation there is a non-trivial solution to our linear system. Yeah. Because we're only interested in finding non-trivial solution. We're not interested in trivial solution, right? Yeah, yeah. Trivial is useless. So we're not interested in the trivial solution. So we want to find non-trivial solution. You want to find non-trivial solution? This theorem tells us its determinant must be 0. Yeah. Its determinant must be 0. Yeah. Otherwise, if determinant is non-zero, non-zero means A is invertible. If A is invertible, that means you only have trivial solution. Okay, that's the logic. Okay, yeah. So, all right. So now we must. So this equation is important. Okay, yeah. This equation. Yeah. Let me write it here. This equation, this determinant, must be 0. Okay, must be 0. Yeah, there you have this equation. This equation is the same as our old characteristic equation, right? Yeah, here you can see. Yeah, the old characteristic. This is our old characteristic equation. Then, when you move to the linear system context, okay, environment context, you get the determinant of this coefficient matrix equals 0. And this equation we call the characteristic equation of this matrix version of the linear ODE. Yeah, linear ODE, we can also calculate the characteristic equation. What's the definition of characteristic? This determinant of that equals 0. That's the characteristic equation of this linear system. Yeah, yeah. Okay. Yeah. Yeah. All right. Yeah. Yeah. So that's our understanding. Okay. So we try to. So you try to use your logic to understand. Yeah. Here in math results, yeah, based on my personal experience. Yeah. Yeah. Because many times I can memorize math results quite well. You know, comparing with my friends, you know, other people nearby, most those people, they cannot memorize math results easily. But for me, I can memorize a lot of math results easily. It's not my memory is better than other people because I use logic to, after I understand the logic, then I can memorize the results easily. But most people, they do not use the logic to help them memorize the results. Yeah. So that's my experience. So if you want to memorize, you know, all these results well, so you need to follow the logic. Okay? Yeah. Yeah. So then it is very easy. Yeah. All right. Let's continue. Yeah. Linearity principle, basis, and a round scale. Yeah. That's our old concept, right? Yeah. So we can move a little faster, yeah, because nothing new. We learned linearity principle, we learned the basis, and we learned the round scale. Okay, yeah. So here we just quickly review. Yeah. All right. So this is the homogeneous version of our linear system. Yeah. All right. So the coefficient matrix. Yeah. All right. Then the superposition principle or linearity principle. Yeah. If you can find two solutions, yeah. Here you can see our notation. We need to use the slightly different superscript. Yeah. Here, yeah. So last time I also talked about this. Yeah, because the notation, when we move to this topic, we should use our notation very carefully. Yeah. Here, that's one thing, because here we cannot use subscript. Yeah. If you use subscript, yeah, we already use subscript y1, y2, right? If you still use y1, you get confused. Yeah. So here people use superscript, but superscript. So we don't want to confuse the superscript with the with the power, right? Yeah, the power exponent number. Yeah, so that's why we put a parenthesis around. Yeah, parenthesis. Yeah, parenthesis. But parenthesis sometimes confused with the derivative, right? Yeah, so that's another possible confusion you may have. Yeah, but we need to use the context to help us separate. Yeah. So which one is derivative, which one not derivative? Because here in this topic, the derivative we use only prime, right? Yeah, only first order derivative, prime. Yeah, that's enough. We use the prime. So we will not use high order derivatives. Yeah. So based on that understanding, so we don't worry confusion with the derivative, superscript, parenthesis. Yeah. All right. Yeah. So the y sup 1, y sup 2, two solutions of the homogeneous. Yeah. Then based on the linearity principle, we can write a new solution. Y equals the linear combination. That's our linear combination. C1, here you see, C1 is a scalar number. Yeah. Yeah. It's not a boldface. Yeah. Yeah. When you see the notation, C1 not in boldface. Yeah. We treat it as a scalar number. Okay. C1 times the first solution, y sup 1 plus CO. The second one should be C2. So I yeah. Oh, you see this blue borderline box because I took the screenshot from our textbook. Yeah. Sometimes the textbook has some mistakes. Yeah. Here, this C2, this is a typo. Yeah. In our textbook. Okay. Yeah. I found several. Yeah. Several typos. Yeah. In our textbook. Yeah. This is one. Yeah. So the linear principle. Then the basis. Yeah. So the basis concept. Yeah. Because we want to represent a general solution, so we want to find the basis of this linear system. Okay. Yeah. All right. So a set of n linearly independent solutions. Y sup 1 dot 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 y sup n. Yeah. N. Linearly independent. Yeah. So you know the meaning of linearly independent, right? Yeah. So we talked about that concept before. Yeah. All right. Yeah. So then the general solution can be represented as a linear combination of these n solutions. Yeah. And the good thing is this general solution representation, this general representation covers all the possible solutions. Yeah. That's the nice thing. Yeah. Yeah. No solution. If we take this linear combination form to represent the general, then we won't miss any solution. That's the nice thing. No solution missing. Yeah. Yeah. That's good. Okay. That means we only need to find the basis, the n solutions, linear independent solutions, yeah, the basis, then we're done. We solve the whole linear system. Yeah. All right. Yeah. Yeah. Arbitrary constant. Yeah. All right. Fundamental matrix. Yeah. Another concept. Yeah. So, what's that fundamental matrix? Yeah. This matrix must be fundamental, right? Yeah. So what's that? Yeah. So that is very simple. Fundamental matrix. Yeah. We take M. Yeah. So we define this n by n matrix. We use the capital boldface capital Y fundamental matrix. Boldface. That's capital Y. Okay. It's a matrix n by n. But how do we form this n by n matrix? We put together the n solutions that form a basis. Well, n solution form a basis. we put them one by one. Yeah, so each solution we use it as a column matrix. A column, column vector. So we have n column vector. Each one has n components, right? Yeah. So horizontally n rows, vertically also n. So this fundamental matrix capital Y boldface is an n by n matrix. Fundamental. Okay? Yeah. All right. Now let me ask you a simple question. Yeah. For understanding purpose. Yeah. Given a linear system. Yeah. So this is a linear system. Yeah. Now we want to consider its fundamental matrix. Okay? Yeah. So you know the definition. Fundamental matrix. The question is the fundamental matrix for this linear system, ODE, unique or not? Unique or not? Fundamental matrix of a homogeneous linear system. Unique or not? Yeah. Can you say something based on your understanding? Yeah. Unique or not? Because in my concept question, quiz, remember quiz concept, this kind of question, I may ask you questions like this, okay? Understanding the concept, yeah, based on the definition. Yeah. Yeah. You need to apply your knowledge, okay? Understanding, yeah. See, is it unique? Yeah. Or the solution is because the fundamental matrix, we use the solution that form a basis. You need to ask if the basis of a solution, a basis of if that basis is unique or not. You need to ask that. Okay, basis unique or not? Can you find another different basis? Yeah. Yeah. Right? Yeah. Think about that. The basis is not unique. Okay, the basis is not unique. You can find a different basis. Okay? Yeah. You can easily find a different basis. Yeah. For example, yeah, think about this is a fundamental matrix. Suppose we already have a fundamental matrix. If you multiply it by 2, is it another fundamental matrix? The simple way. Yeah. 2. You double it. Okay? You double each vector, still fundamental matrix, right? Because if y1, y super 1 is a solution, if you double it, 2y, is it another solution? Yes. When you double all these vectors, they are still linearly independent, right? Yeah, they're still independent, okay? All right. Actually, here I can tell you one thing. Yeah. When you have a fundamental matrix, capital Y, now, I just multiply another matrix. Yeah, let me see, B times Y, capital Y. If this B is invertible, you know the meaning of invertible, okay? If B is invertible, then B times Y, it's another fundamental matrix. Another fundamental matrix. Sorry. No, not B. Yeah, not that. Yeah, because that's scary. That's scary. Okay, that's scary. All right, because B invertible matrix, scary. There is a condition. There is a condition. Then B times the fundamental because there is a condition. Yeah, that's an important condition. What's that important? B should be commutable with A. So B times A equals A times B. If we add this condition, B and A commutable, then it's correct. Another fundamental matrix. But if not commutable, then you cannot say that. Okay? That, yeah, it's wrong. Yeah. If not commutable, it's wrong. Yeah. Because the reason you can see it, it's very easy. All right. Because fundamental matrix each, yeah, so here, yeah, let me write, yeah, because this kind of question very likely appear in your quiz questions. That's why I spent some time to help you understand, yeah, from many different angles, try to understand better, yeah. So we build a solid foundation, yeah, and a linear algebra, solid foundation, yeah, before we, continue to solve our many other problems. Yeah. All right. Yeah. Solution. Let me use J. Okay. Superscript parenthesis J. We know this is one of the solution vectors. Okay. All right. Yeah. Because it's a solution. Do we have a derivative equals a times yj sup? We should have that, right? Yeah, we should have that. Okay, yeah, yeah. Plug in, yeah. We just take arbitrary one of the n solutions. We plug in, yeah. The equation must hold. All right. Now I apply this. I make this j from 1 through n. Okay? I apply n times, each time with a different j superscript. Okay? All true, right? All true. Can I put all those things together? Can I pack them? Okay? The first one is sup 1, but prime, okay? Yeah, I do not write the parentheses. Save some space, okay? The second one is sup 2 prime, also prime, yeah? Pack them one by one, okay? As column vectors. The last one, n, but prime, okay? Pack in that way. Can you see we can factor the matrix out inside the no prime version, yeah? 1, and can you see that? Yeah. Yeah. Just put them together, right? Yeah. Put them together. Yeah. But column-wise, if you compare column from both sides, column-wise, they are equal. Okay. Now you just pack those columns together. Yeah. That's true. No problem. It's true. All right. Now, can you see? This matrix is that our fundamental matrix, capital Y. Capital Y, right? See? Yeah. That's by the definition, capital Y. And left-hand side, is it a derivative of capital Y? Right? Derivative of capital Y. How do you take derivative? Column-wise. Okay? Column-wise. Or row-wise, it doesn't matter. Because each entry you take derivative, right? Each entry you take derivative. You can write column-wise or row-wise. Yeah, same thing. Yeah. Will you get capital Y prime equals capital A times that Y? Capital Y? Yeah, right? So you get that, right? Okay, yeah, that equation. It's true, yeah, this time. Matrix multiplication, okay? Capital Y prime equals capital A matrix times the fundamental Y matrix. All right. Now, suppose there is a B matrix. Okay. This B matrix is invertible. Invertible. Okay. The first condition. The second condition, this matrix is commutable with A matrix. Commutable. Two conditions. Okay. Now, can I multiply B matrix both sides? Multiply this equation both sides? Yeah. B times Y prime equals B times A times Y. Yeah. Multiply B matrix both sides. Yeah. Yeah. The same. All right. The same. B, because B is a constant, right? Constant matrix. B times Y prime, can we write the parenthesis, yeah, let me use a space here. B times y, put a parenthesis outside. I'll put a prime operator outside. Yeah, constant, we can take it inside, outside, derivative, right? Yeah, derivative, we can do that. Yeah, inside, outside. Yeah, just like a constant, okay? All right, then this side, BA. Can we write a BA as AB? Yeah, because commutable, right? So here, this property is important. If you don't have this commutable property, then you get stuck. You cannot do anything, okay? Yeah, so that's why we need to add this extra condition. Commutable. Commutable, we can write A times B times Y. Okay? A times B times Y. Then, because now B matrix is adjacent to Y matrix, can we group them together, treat as a new matrix? B times Y matrix. Yeah. That's, we use the associativity. Yeah, is it associativity? Yeah, associativity, okay, property. Associative. Yeah. So we associate B with Y, all right? B with Y. Yeah. Now, can you see B, Y, this is another fundamental matrix? Yeah, because it satisfies the same equation, right? So capital B times Y satisfy the equation. And here, why I add this B is invertible? Because if B is not invertible, then you use B multiplied by Y, the whole new matrix won't be invertible. Okay? Yeah. Because you get a non-invertible matrix. And our fundamental matrix must be invertible. Because it's from a basis, right? So this solution form a basis. Basis means this whole matrix must be invertible. Then you have the basis. Basis must be linearly independent. Independent, you put n linearly independent vectors in a matrix, that matrix must be invertible. Okay? Yeah. Otherwise, if it's not invertible, those matrices will be linearly dependent. Because you can find the appropriate coefficient. Yeah. K, yeah, remember? So we can find appropriate K1, K2, Kn. Okay? Yeah. If the matrix, this capital Y matrix is not invertible, then you can find the K1 K, such that K1 times Y1 vector plus Kn Yn vector equals 0. Yeah. That means they are linearly dependent. Yeah. Non-zero. Yeah. So these K not all 0, okay? Yeah. So there are some non-zero numbers in this set of K coefficients. Yeah. 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 So that linear algebra, basic knowledge, okay? Basic knowledge. Yeah. Yeah. Why is that? Yeah. Some of you may feel hard to understand this statement, this result. Just use our previous slide. Remember, before the break time, I used the previous slide. I talk about invertibility. I talk about non-trivial solution. I talk about all those things. Yeah, you can combine. You can connect with this conclusion. Yeah. If later I have time, I will elaborate. Okay. Yeah. Today I want to save a little. Yeah, because we don't have too much time. Today I don't want to waste too much time on this. Later, at some point, I will explain this. If you couldn't see it, if you couldn't see why my conclusion is like that. Oh, probably, yeah, at some time. So when I do review, yeah, because all these things I feel very important. When I do review, I want to give you a long list of statements. Okay, yeah, because here I talk about many statements. I try to compile, put it in a one page, okay? I list them in one page, yeah, all those statements. Then we go through, yeah, study, I explain, yeah, for each statement, y is that. Yeah, yeah, because here I said many things. Yeah, yeah, yeah. At some time I will put together. Yeah. All right. Yeah. So here, the general solution here. Yeah. So what's the general solution? Yeah. Why this fundamental matrix is useful? Because any general solution, yeah, here, Y, any general solution can be represented as a fundamental matrix capital Y multiply a C vector. Yeah. That will be one of the general, because C vector, you have freedom to choose the components, the numbers for the components in C vector. Yeah. Whatever you choose, you will get a different solution. Yeah. So that's the importance of this fundamental matrix capital Y. Okay, all right. Yeah. All right, the Wronskian, yeah. So what's the Wronskian? Yeah, that's simple. After we define the fundamental matrix, then the determinant, you can see, yeah, here, I erase, my calculation. Because later sometime we will do the similar calculation. Yeah, later, okay, yeah. Yeah, so here, what's the Wronskian? Wronskian is just the determinant of that fundamental matrix, right? Okay, see? Yeah. So that's why we define that fundamental matrix, okay? The Wronskian. Yeah. And we know the Wronskian of a fundamental matrix can never be zero, right? Yeah, because they formed by basis functions, basis solution of the solution. Yeah, basis linearly independent. Yeah, m linearly independent vectors, if you put them in the one square matrix, then the determinant cannot be zero. Yeah. Yeah. That's the reason linearly independent. If the determinant equals 0, then you can say they are linearly dependent. Okay, linearly dependent. Yeah. All right. Yeah. Existence and uniqueness theorem. Yeah. So in first order, second order, we studied existence uniqueness theorem. Yeah. Here, yeah, this general case, let's look at existence uniqueness theorem. All right. Yeah. So we consider this system. Yeah. But this system here, we do not say little f1, little f2, they are all linear functions, right? Yeah. We do not say that. Yeah. So this is a system of ODEs, but may not be linear systems. Yeah. So you should be careful in our assumption if we say it's a linear system or not. Yeah. Okay. Yeah. All right. The existence theorem. Now you can see for the existence system, uniqueness theorem. Yeah. Let f1 ... fn in 1 be continuous functions, have continuous partial derivatives in some domain R of t. Yeah, yeah, because you have t variable, right? So then y1, y2, y space, yeah, containing the point t0, initial, yeah, that point. Yeah. But here we do not say these little f functions, linear functions, right? Yeah, we do not say that. Yeah. Here, so when you read the statements, you should be very careful. Here we do not say linear functions. That means, so this theorem powerful. Why so powerful? Even for non-linear f functions, still correct. Okay? It's still correct. Yeah, yeah. We know non-linear function could be very complicated. Yeah, it can contain y1 square, okay, y2 cube, okay, y3 to the 100th. Very complicated. Yeah, yeah. Don't worry. Still, this theorem still correct. Yeah. All right. All right. Then the system 1, yeah, has a solution on some interval, certain interval, around that t. T is the variable, right? Yeah. T is the, the variable of this equation. Yeah. All right. So then, other symbols, although they have the forms of variable, but they are functions. Yeah. The unknown functions we need to solve for these functions. So in this some interval around that variable t satisfying the initial condition, and this solution is unique. The condition here. So what's the condition? So if you ask, the condition is actually the condition. The main part of the condition. Okay, the main part of the condition. These functions having continuous partial derivatives. That's the main condition. But this part, so there is this part. These functions are continuous functions because if these functions they have continuous partial derivatives, it's much stronger than continuous functions, right? So the second part of the condition, much stronger than the first part. Okay? Because derivatives continuous, much stronger than original functions continuous. Okay? Because the partial derivatives, so your functions, sorry. Just a minute. Continuous. That's correct. So partial derivatives continuous, much stronger than original function continuous. All right. So that's the main condition. Partial derivatives continuous. All right. So that's the existence unique theorem. All right. Then we add a G part. Okay. Known vector. So it's a known vector function. Known vector. Okay. All right. Then existence uniqueness of the linear case. Here you can see when we consider this system, then this part, okay, that's this time linear system. That's a linear. Okay. So the second system, this system number 3, that's the linear system. So this second one is a linear case. Linear case. All right. Let the AJKs and the GJs in equation 3 be continuous function of t on an open interval alpha less than t less than beta containing the point t equals 0. Then 3 has a solution y of t on this interval satisfying 2 the initial conditions, and this solution is unique. Then for the second theorem, we just apply the first theorem, because we know when we have the condition, these functions continuous, because we can take partial derivative easily, right? We take partial derivative, still continuous. So that's why we apply the first theorem directly on the second. Second one you can consider as a corollary. Okay, corollary of the first theorem. Just straightforward. Apply the first theorem. Because partial derivatives all continuous. Original function also continuous. No problem. All right. I run out of time. Today, I spent a lot of time on basics of linear algebra because, based on my experience last year, it's so important. Especially build a solid foundation to help you understand the remaining part of the materials. All right, so let you go. So that's it for today.